Hi, in the previous mini lecture I have introduced 1-bit memory on the example of SR latch. I have presented two versions of SR latch. I mean 1-bit memory, and the versions were asynchronous and synchronous one. In general, all 1-bit memories can be divided in this way. This is the family of asynchronous devices, asynchronous memories, and synchronous ones. And then the asynchronous one can be only latches. Their name are latches, and there are 4 different types of latches. SR, D-type, T-type, and JK. The same is true for synchronous devices, synchronous memories, but here you can find 2 sub-branches of these. One branch on one family is called latches. It's very similar, the same name as in the asynchronous version, and the second family is called flip-flops. What's the difference between? Synchronous means that there is a clock input to each of the memory device, and they can operate only if there is an active event on the clock signal. And these events can be divided in 2 groups. There is a change in level, so these are active when there is an active level. There can be 2 levels, of course, 0 and 1 levels, and they are sensitive, and they can operate when there is a given level on the clock. And flip-flops can operate only when there is an edge, and in a very small period of time when there is a change of clock. And there are 2 possibilities as well. There's a rising edge and falling edge. So they can be divided as rising edge triggered and falling edge triggered. And in each of the family there are 4, and also for latches there are 4 types of memories, 1-bit memories, and they are called and operates in the same manner as are. Yes, the difference is when they can change their states. These in the period of clocks, and this only on edges. They are strictly synchronous, and we as designers rather use flip-flops than latches. And of course, from time to time you must use latches for some reasons. Okay, so we are in the course, we will not be dealing with asynchronous variants of the latches. We are only interested in synchronous parts, synchronous versions of the 1-bit memories. So independently of the type of triggering, independently of their latches or flip-flops, the description of them are the same and only depends on the type. They are S, R, D, T, or JK. So let's start describing synchronous flip-flops and latches. the descriptions are the same independently of the type of triggering. So let's start with what you already know. It is a SR flip-flop, which has two inputs, S and R, which are called set and reset. And there will be also clock, or CK for short, not CLK, CK. Let's decide, and Q and not Q on the outputs. And there is a symbol, is it the first way to describe it, next how it works, and STT, state transition table, short one, gives you a very compact description of how it works. You've got only two inputs. The clock input is not present in STT, and 10, sorry, and 11, and you should put Q of t plus 1. What it means plus 1? After one clock impulse, after the next clock, okay, after change has occurred. So after it was allowed to operate, wasn't blocked by clock. So it is clock pulse. That means that you've got a low level, high level, rising edge and falling edge. All the possible conditions had occurred, and then you put in the table what was the next state. And the state before the clock impulse is denoted by Q of t. So before clock, so the current state, in other words, in the current state is Q of t, and the next state after clock is Q of t plus 1. Can be different or the same, depending on what the input conditions were during the clock, the active clock. Okay, so SR, as you remember, is a memory. Don't change your state. So Q of t plus 1 is exactly the same as Q of t. R is the reset. Reset means 0 in a memory. Set 1 put into the memory. And 1 is not allowed. Okay, not allowed. Never do it. So your task is to control it, not having 1 at any time. All right, so this is the second way of description. The third way is to deliver STD as a diagram, as a graphical form to present the changes of the state of the memory, the content of the memory. There are, of course, two possible contents of the memory. The memory output is this, it is simply Q. So what's inside these circles are all possible values of Q output. Not the inverted one, but this is not inverted. Okay, and then looking at this table, you draw arrows to show the changes of the states in all the possible conditions on the input SR. 0, 0. To draw what is happening when you put 0, 0, you simply analyze this. It means that if you are in the state 0 and you've got 0, 0, the state doesn't change, so you must put arrow towards the same state. Okay, and it's a loop, and you put SR equals aside this arrow 0, 0. Okay, the first bit on the left will be S, and the second on the right hand side R, and the same is true for state 1. 0, 0 is here as well. Okay, because if you have the current state Q of t 1, you will have the same state after clock. The second line gives you the what is happening when you put a reset. if you are in 0, the reset doesn't have any influence on the content. Was 0 and will be 0. So you put aside the same after comma. You put the second condition for the same change, 0 to 0. If you are in state 1 in the memory has 1 in its content, you change it. You must change it and show it on the diagram for 0, 1 for reset. Simply resets this. So the second is already done, and the third is setting. Setting, when you are in state 1, doesn't change anything, but if you are in state 0, the content of memory is 0, you'll get 1. It is a change because this is a set command. And the last one is not present here because this is not allowed. Okay, so that's the state transition diagram. And the fourth way is to deliver the equation for this state transition equation. In order to do this, you simply put, in order to have it in the minimized form, you put the SR and current state Q of t, the current state. And your task is to deliver the equation for Q of t plus 1 for the next state. So for this. So 0, 1, but in terms of 0, 1s, the best way to express it is as the Carnot map, and you put, if you've got S0, don't change anything. It is a reset command, it is a set command, and it is not allowed, but you can use it, yes, with the additional condition that SR as times ended with a must be 0. So 1, 1 is disallowed. And now you simply minimize using ones, for example. You've got two groups. So Q of t plus 1 equals. From the first you get S, plus from the second group you've got Q of t times not R. Q of t times not R. It is the state transition equation for SR. Flip-flop or latch. Doesn't matter which one is it. Then the next one is the D-type, is the simplest one, containing only, having only one input Q, apart from CK, and Q, not Q, as usual. Okay, and this is the simplest. Simply you put what you want to get on the output. So Q of t, let's start with the very simple state transition equation, which is simple. Q of t plus 1 is equal to t dt. And that's it. Simply copy the input into the output. What you put, you get. Okay, so state transition diagram is the following. These are values of the memory Q. Yes, it is this signal. And if you have 0 on input, you will get 0. If you have 1, you will get 1. And the same is true here. If you have 0, you will get 0. And if you have 1, you'll get 1. And the state transition table is also very simple. D and Q of t plus 1 is the following. If you get 0, you'll get 0. If you put 1, you will get 1. That's it. This is the simplest latch or flip-flop. You must know by heart all the possible descriptions I've just presented for S, R, and D, and in the following mini lecture I will present two other types of the flip-flops, so the one-bit memory elements, which are called T-type and JK type. Thank you.